So we're going to use Kirchoffs law to justify the addition for resistors when they're wired in series and when they're wired in parallel. So first, these two words, we have to clarify what those mean. So I'm going to draw two diagrams for you. One is going to be a 10 ohm resistor and a 40 ohm resistor wired in series. So series, you've maybe come across as like television series or a series of books, means that they come one after another, after another, after another. So you start at the beginning and you end at the end, and you read everything in between. So in a circuit, the symbol for a resistor is just this weird like squiggleized thing. Alright, so I've got 10 ohms there, and I have 40 ohms there. The other option is that if you have a 10 ohm and a 40 ohm wired in parallel, well, that would look like this. 10 ohm and 40 ohm wired in parallel. So in a parallel structure, the current doesn't go through one, then the next, then the other. It either goes through one branch or it goes through the other. So you would have a conductor coming in and then it splits. And one of these things is up here and one of them is down here. Maybe we'll put the 10 on the top and the 40 on the bottom. Alright, so we're going to use this idea of Kirchoffs law. Now, whoever Kirchhoff was pointed out the pretty obvious fact that if there's current going through the wire this way, any current that passes through this resistor has to then pass through this one as well. There's no branch around that. So any current through here must go through there. Make note of that. Current here, current 1 has to equal current 2. Alright, so if you think about Ohm's law was, let me jot that up here, that voltage was the current times the resistance. So in this particular resistor, the voltage that it will consume will be 10, its resistance, multiplied by this current, whatever that is. And this one here will be 40 multiplied by its current, whatever that is. But then these two things actually add to, are identical. So that's the same as 40 times the current through number 1. And if I were to add up these voltages, right, like the voltage consumed by this and the voltage consumed by that, that should be the total consumed. Voltage through 1 plus the voltage through 2. I have 10 here, and I have 40 here. Now 10 and 40, I have an I1 there. So whatever this current was, I can factor it out of this, leaving 10, and I can factor it out of that, leaving that. So I'd end up with 50. So just by using the algebra structure of Ohm's law and combining your two voltages, the fact that these currents have to match means that you can get the total resistance of that circuit by just adding the two pieces together. And that should make some sense. If you put 10 ohms in the way of your current, and then you put another 40 ohms also in the way, then there should be 50 ohms of resistance in total. So I'm going to erase this yellow stuff, and I'm just going to summarize it that way on the screen here. So because the current through the 10 ohm must match the current through the 40 the total resistance is just the sum of all the resistors. So in English, if you have a 10 and a 40, you add them together to get 50, which I had calculated here already. Now, if we go down to this one, when it's wired in parallel, and you have a choice. Some of the current is going through this up branch, and some of it is going through the lower branch. And if you think about that, there should be more current going through this one, because there's less resistance. So whatever voltage is applied to this, hook it up to a 9-volt battery or plug it into the wall, whatever you're going to do, we're applying some amount of voltage to this. That voltage is either absorbed entirely by this one, or it's absorbed entirely by that one. And because a voltage drives more current through a smaller resistance than it does through a bigger one, I should get more electrons choosing that path. When you're doing the total resistance of a parallel structure, you have to use a funny little calculation. So I'm just going to do it first, and then we'll try and justify it using Kirchhoff's law. So if I was to try and find the total resistance of this, the basic rule is that 1 over the total resistance of the circuit is equal to 1 over the first resistor plus 1 over the second resistor plus 1 over the third resistor, etc. So in this particular diagram, I only have 2, so I don't need this or any of the ones that came afterwards. My total resistance would be 1 over 10 plus 1 over 40. Now, if you're the kind of person who finds fractions a little stressful, that's okay. You can just go to decimals. 1 over RT is 1 divided by 10 is 0.1, and 1 divided by 40 is 0.025, I think. So 1 over total resistance would be 0.125. Now you notice that that's 1 over RT. I have to flip this, or I have to do some algebra to move it around. So I'm going to just do that up here. If 1 over RT equals 0.125, then 1 is 0.125 RT. I just multiply this up into the numerator. Divide both sides by 0.125, and 1 divided by 0.25 is 8. So the total resistance of this little structure here is 8 ohms. So I want to do that again, but I want to do it with the fraction method just so you can see. And then we'll maybe shorten the fraction method up in order to make a general formula for this, if that will be a bit easier. So I'm just going to erase a little bit of this. So if you're trying to do fractions, you can't add two fractions unless you have a common denominator. So I see 40 here and I see 10 there. I could make this a 40 if I quadrupled both in the top and the bottom. Now that they have matching denominators, right, 4 40ths and 1 40th, well, that adds up to 5 40ths. And I notice that this fraction is upside down, so I could fix that if I took both fractions and reversed them. So I'd end up with RT equals 40 over 5 instead, and 40 divided by 5 is 8 ohms in total, which is what I had going there. Alright, so if I were to try and do this in general, I'm going to get rid of these. I'm going to try it without putting any numbers in. I'm going to start with just two terms. So this denominator has an R1 in it, this denominator has an R2 in it. This doesn't match this, but it would match it if I introduced an R2 along with it. But if I multiply the bottom, I have to multiply the top as well. This fraction already has the R2, it needs the R1. So I'll introduce the R1 to the bottom. But if I introduce the R1 on the bottom, I have to introduce it on top as well. This is just common denominator basic fraction operations. R2 of these plus R1 of those would be R2 plus R1 of these. Well, that's handy. And if I have to flip it then, the total resistance would be, instead of this in the denominator, it's now in the numerator, R2 R1 over R2 plus R1. And if I tried this for this particular circuit, resistor 2 was 40, resistor 1 was 10, resistor 2 was 40, resistor 1 was 10, I end up with 40 times 10, which is 400, and 40 plus 10, which is 50, and 50 fits into 400 8 times. There's that answer again. So if you're trying to find the total resistance of two resistors wired in parallel, you could just use this, and that's okay. Or you could use this, and that's okay too. So if I try and do this for an R3, 1 over RT, this thing needs an R2 and an R1. This thing needs an R, sorry, I gotta put them in there, R2, R1. This thing already has the R2, it needs the R3 and the R1. And this thing already has the R1, it needs the R2 and the R3. So I end up with 1 over total resistance is, well, this many plus this many plus this many would be R1, R2 plus R1, R3 plus R2, R3 over R1 times R2 times R3. Now that's getting to be a bit much. This is a formula you're going to have to memorize. Oh, and I've also got to flip it still, don't I? So that the total resistance, flip this side, so I have to flip this side, is R1, R2 plus R1, R3 plus R2, R3, all underneath of R1, R2, R3. We just keep saying that word R over and over and over again. It stops making any sense. It makes me sound like a pirate. What was I saying, right? Like, this is gross. And that's something you might park on a formula sheet, and you are welcome to do so. You're never going to remember that. You can maybe look at it and see some patterns, like if you have three things, you can either take this and this, this and this, or this and this, and those are the only combinations available. And that's what these three things are. 1 with 2, 1 with 3, 2 with 3. That's all the ways you can combine them. And then the top is just the product of them. Or you can remember this line, where you're just doing 1 over this thing, plus 1 over this thing, plus 1 over this thing. It's really up to you. So now I've got to do a little bit of justification for how all this worked out. Alright, so back to Ohm's law to try and convince you that this 8 was correct. If I were to try and calculate the current through this particular resistor, I'd use Ohm's law. I don't know what the voltage is, but whatever, it's a number. Voltage through the 10. And that would give me my current through the 10 plus, nope, not plus, multiplied by the resistance of that 10, which is just 10. I'm going to write them in this order so it's easier to see. Now if I were to try and calculate the current here, I just need to divide by 10. So the current passing through this thing is whatever the voltage is divided by the resistance. And that's just Ohm's law. We did that the other day. We're going to do the same thing for the 40. Using Ohm's law, the voltage through the 40 is 40 times the current through the 40. So the voltage it's experiencing divided by 40 should be the current through 40. Okay? Now, here's where Kirchoffs law comes in, is that the total current, remember last time it said all the current, if it went through this one, it had to go through that one? Well, in this structure, some of it goes this way and some of it goes that way, but it all has to add up to what went in and what came out. Right? Electrons can't get lost. So if 50 of them went this way, and you figure out later that 20 of them went that way, then 30 must have gone here. 20 and 30 is the 50 that you started with. So your total current has to be the current through your 10 plus your current through the 40. So, fine. The total current, if I rearrange Ohm's law, is voltage divided by resistance. So the total voltage divided by the total resistance would equal, well, there's the expression for the current through the 10. It's the voltage experienced by the 10 divided by the resistance plus the voltage experienced by the 40 divided by 40. And remember, way back at the beginning, when I just introduced this idea of parallel, is that this battery dumps all of its energy on this one or on this one. So if this is a 9-volt battery, then this resistor must absorb 9 volts because there's nothing else in the pathway to absorb it. And this resistor must also absorb 9 volts because there is nothing in the pathway to resist it or to take any of the extra. So the total voltage then is equal to this and equal to that, which means they divide each other all out. And I just got to leave a little placeholder there, because V divided by V is 1, V divided by V is 1, V divided by V is 1. And I get this very familiar thing again, right? 1 over the R total is 1 over the resistance of resistor 1 plus 1 over the resistance of resistor 2. So that's where this comes from. What you need to be able to do is to look at two resistors in series and say, I know, I just add those up. 10 and 40 is 50. When you see two in parallel, you need to recognize that you have to use this sort of structure or this sort of structure in order to get it done. So I'm going to do a few examples of more complicated resistors wired in series and parallel, and then we're going to come back, then you should be ready to do some of the practice problems. All right. Okay, so if you're trying to do a 15 ohm resistor in series with a 25 ohm resistor, first thing you need to do is draw it. So here's my 15 ohm, and here's my 25. And if it's in series, it means it goes from the beginning into one, into the other, and out. So any current that goes through this has to also go through that. So when I see these here, the total resistance in a series circuit is just the resistors added together. So 15 plus 25 for a total of 40. No problem. What if they were in parallel? The same numbers, but in parallel. All right. So if I were to draw those, I'd have my 15 and I have my 25. And if it's in parallel, then there has to be a pathway that goes through the 15 and not the 25. And there has to be a pathway that goes through the 25 and not the 15. And they have to be connected to the same power source. Now that looks really gross. But you can see I go from the battery through the 15 and not the 25, from the battery, miss the 15 through the 25. That is drawn in parallel. So the way you do this type of resistor is you do 1 over the total resistance is 1 over the first one plus 1 over the second one. 1 over the total resistance would be 1 over 15 plus 1 over 25. Now you can go and you can flip to decimals at this point, so I'm going to do it that way first, and then I'll go back and do the fractions. 1 over RT is 1 divided by 15. And you're going to see in a minute why the decimals are not a good idea. 1 divided by 15 gives you 0.06667. It actually goes on sixes forever. 1 divided by 25, 1 divided by 25 is 0.04. Plus my 0.6667 is 0.10667. Pop this up here. 1 equals 0.10667 RT. This goes underneath. And 1 divided by that number is 9.3747. So if I add them up in parallel, then this structure only resists the battery with this much resistance, 9.3747. Alright, now if I tried it with fractions, let me clean this mess off here for you first. 15 is, that's 3 times 5. 25 is 5 times 5. Notice how this has a double 5 and this has a 3 with a 5. So this one is missing a 3 on top. No, it's missing a 5 on top. So the 3 that was already there, the 5 that was already there, and a new 5 that I just introduced. This one is missing the factor of 3, so I'll introduce it. Now they have common denominator now, so 5 of these and 3 of these would be 8 of them. And 5 times 5 is 25, times 3 is 75. So my total resistance, oh, I'm not done yet, I have to flip. And so I end up with 75 divided by 8, which is 9.375. Now, when we did this before, we had 9.374 or something, and a whole bunch of garbage going after it. The rounding error ended up turning this into some awful long decimal when it should be a nice clean number. So the fraction method is strongly recommended because it gives you a nice clean value. You could even just leave it as the fraction if it comes out as something gross. I'm going to use the formula just so you can see how that works as well. So if you wanted to use this formula, which is specific to 2 resistors wired in parallel, you could do that. So if I'm going to part those numbers in, R1 is 15, R2 is 25, R1 is 15, R2 is 25, and 15 times 25 is 375. 15 plus 25 is 40, and 375 divided by 40 gives you, lo and behold, 9.375 ohms. So you have some choices. You can either use this little equation for 2 wires or 2 resistors wired in parallel, or you could do 1 over RT as 1 over R1, 1 over R2, 1 over R3, and add them with fractions, which will give you a clean answer. Or you can use 1 over RT, 1 over R1, 1 over R2, etc., and use decimals, and it will give you an approximate value of this. And it doesn't really matter which method you choose. You saw me do it 3 ways. At least one of them will really speak to you, right? Like, that's the way for me. And you can choose that and do that from now on in, and that's fine. It doesn't matter. Alright, so we've done these in series, we've done them in parallel. Let's try some more complicated ones. Alright, so taking a look at this one, I have a 20, I have a 30, and I have a 50. And so you have to decide whether they're wired in series or if they're wired in parallel. So if I were to trace along this particular thing, all the currents, there's a pathway that goes here, it goes through the 20 and out. And there's a path that comes through here, goes through 30 and out. And there's a path that goes down here through the 50 and out. So you can see that all three currents are present in this particular part, and all three currents are present in this particular part, but on each individual branch, each resistor is only getting one current path. So that's the definition of parallel, right? You can go this way, or you can go this way, or you can go that way. So I have three resistors that I have to add up in parallel. So I'm going to have to grab that weird thing that looked like this. 1 over RT plus 1 over R1 plus 1 over R2 plus 1 over R3. And there is a bigger, more complicated formula. Maybe you wrote it down. It was in the video earlier, so you can rewind and find it there if you like. I'm not going to use it because I think it's just as fast to do this manually. So 1 over the total resistance would be 1 over 20 plus 1 over 30 plus 1 over 50. Okay. So what are we going to turn these into? Well, let's just do decimals. 1 divided by 20 is 0.05. 1 divided by 30 is 0.03333 forever. And 1 divided by 50 is 0.02. So if I add those all up, I'm going to get 5 plus 0.03333 plus 0.02 is 0.10333. And so RT comes up .033 goes under. My marker quits mid-thought. And 1 divided by that number is 9.6777 ohms. So this structure here, even though it contains a 20, a 30, and a 50, is only going to provide 9.6777 ohms of resistance in total because of its wiring in parallel. That's weird. If you go back through and you look at all the other examples we've done of parallel, that was true. That the total resistance ends up being less than the lowest resistor that you wired in there. It's just sort of bonkers. But that is the way it works. So you can try and wrap your brain around that somehow. Now, if I took those same three resistors, 1, 2, 3, and I put them in series, 20, 30, 50, and I tried to calculate my total resistance there. Because it's in series, the total resistance will be R1 plus R2 plus R3, which would be 20 plus 30 plus 50, giving me a total of 100. So if you put them in series, then they all help each other, and you end up with 100 ohms total. If you put them in parallel, there seems to be some sort of conflict between them, and it only net results as about 9.7-ish ohms. I'm going to do this one. I'm going to try and do it in fractions, just so you can see how that is. Okay, so 1 over 20, let's see, that's 1 over 2 times 10. This is 1 over 3 times 10. And this is 1 over 5 times 10. So this thing has a 2 down here, and it doesn't have the 3 and the 5. So I'm going to put that in. This one is missing the 2 and the 5. So we can put them in. I guess there's a 10 in there too. And this is missing the 2 and the 3. So 2 and 3 and 5 and 10. So 3 times 5 is 15, 2 times 5 is 10, 2 times 3 is 6, 2 times 3 is 6, 6 times 5 is 30, and 30 times 10 is 300. So I end up with 25. I end up with 31 over 300. That's 1 over RT. So RT would be 300 over 31. Now, that's it. That's the answer, and that's exact. Now, if you've ever tried dividing by 31, you know this is going to be a mess. But 300 divided by 31 gives us 9.6774. 6774. And I think the rounded answer from before was 9.6777. So we're off by 3 ten-thousandths of an ohm. Maybe that matters, maybe it doesn't. I think for us, just doing these calculations, it doesn't matter. So if you prefer the fraction method, go ahead. If you prefer the decimal method, you're welcome to do that as well. All right. So that's very complicated looking, but this is how electronics are wired, right? You'd have 2 components that need to draw this amount of voltage, and then you have some sort of knob to control the volume, right? Like you can increase this resistance or not to affect the whole circuit, and then you have 3 other pieces that just absorb what's left. So many components all in one circuit, and now we have to figure out what the total resistance is of this monster. So the first trick then is trying to identify what's in series and what's in parallel, because there is a mixture of things here. So if I start a pink path, I'm going to start drawing the pink path here. I'm going to go through that, and I'm going to go down through this, and then I'm going to do this, and then out. Alright, I'm going to draw a blue path. Markers make horrible sounds. There's another path. And one more. So here I don't have a split, so well, here's where it gets complicated. If I start here and I go through this, I've already counted for that pathway, and I've already counted for that pathway, so it either goes up or down. Then it must pass through this pathway. But I don't have a choice there. And then down here, there's still a pathway that's unaccounted for along this particular circuit before leaving the system. So the point of drawing those, and you don't have to every time, is I can see that at this point the current split. So these 2 things are in parallel up here. Parallel starts with P, not with R. But this piece here, no matter which branch I took, whether I took top or bottom, I had to go through this resistor. If you must go through it, then that thing is wired in series. And then when I got to here, I had 3 options. I could go that way, or that way, or that way. So once I got into that, this thing is parallel again. And again, parallel starts with P. So I have to do a parallel structure here, and I have to do a parallel structure here. So I might as well just do them and get them out of the way. So this first one, 1 over RT, is 1 over 10 plus 1 over 40. I think we did this already. I think it's 8. That would be 4 40ths. That would be 5 40ths. Flip it, I end up with 40 over 5, which is 8. Lovely. So this thing here, I'm just going to write her in pink. That's worth 8 ohms altogether. Alright, I'm going to erase this, and then we're going to do this one. Okay, so to do the bottom section, 1 over RT is 1 over 80 plus 1 over 90 plus 1 over 70. Now, I don't know about the common denominators there, so let's just try the decimal way. 1 divided by 80 is 0.0125. 1 divided by 90 is 0.01111. I'm just going to keep 3 of them just to match there. And 1 over 70 is 0.0143. So if I add those all together, plus 0111 plus 0125 gives me 0.0379, and this comes up. This goes down. And I get 26.395. So this whole thing here is worth 26.395 ohms. Okay, so I've got my answer. I'm going to try it by fractions. So 1 over RT is, this is an 8 times a 10, this is a 9 times a 10, and this is a 7 times a 10. So this one is missing the factor of the 9 and the 7. This one is missing the 8 and the 7. And this one is missing the 8 and the 9. And that should all be over a factor of 7, a factor of 9, a factor of 8, a factor of 10. So 9 times 7 is 63. 8 times 7 is 56. 8 times 9 is 72. And 7 times 9 times 8 times 10 is 5,040. 63 plus 56 plus 72 gives me 191 over 5,040. Flip them. So that's my exact answer, if I'm interested in exact answers. Equals times 26.387. So I got a little bit off. I know that's correct. That's the exact answers. I didn't do any rounding. So I'm just going to fix this here. 26.387. Good. Well, now I have to figure out what to do with this hot mess. Right now that I've figured out the value of the parallel structure here, and I figured out the value of this parallel structure, now I have this and this and this all wired together. So I'm going to erase this and see what to do with it. Alright, so to figure out what to do with this, I'm going to simplify this diagram. The current comes in this way, and then it goes through this object here. And it's a mess, it's two parallel things, but I just did all this work to find out that it's really only worth 8 ohms. So that's what I'm going to put here, 8 ohms. Then it goes through this thing, which said 60 ohms, and I haven't done anything with that yet. And then it keeps going down, and it goes through this thing, which again was complicated to get the math for, but it's only worth this. Right, I've already figured that out. So I'm just going to draw it like so. That's 26.387 ohms. And then the current leaves. Well, what I've done is I've collapsed all of my parallel structures and left all of the things that are in series still to figure out. So this is really easy, right? Things in series, you just add them together. So the total resistance of this circuit must be the net resistance of this weird parallel thing plus the resistance of this 60 ohm resistor that everyone must pass through plus the resistance of this other wonky structure, and that gives me a total of 26.37 plus 60 plus 8, 94.387. So if you were to attach a battery or plug this into the wall, whatever this is, it's going to resist the current or resist the voltage from that electron source with 94.387 ohms of resistance in total. Now, if you knew the voltage size, and we now know the resistance, you could calculate the current that would flow through this, and then we could figure out the current through each individual component as we go through. And that's the next section, solving circuits, seeing how much current actually flows through each piece. But for now, we're just going to work on collapsing resistors into a single value. So if I were to go through this problem and put these steps in order, because steps are nice. First thing you did was collapse all of the parallel structures. This must be a Monday thing. Parallel starts with P. So basically, I found out what this thing was worth. I found out what this thing was worth. Number 2, redraw the circuit. To see what's in series. Number 3, add the total. All right, so one more example of this, and then I think it's off to the problems. All right, here we go. So I'm supposed to collapse all of my parallel structures, redraw the circuit to see what's in series, and then add the total. So I can see a nice parallel structure here. So I'm going to get rid of that one. Let's see, 1 over RT is 1 over 15 plus 1 over 30. Now that's an easy one for fractions. I just have to double this. So that's 2 30ths plus 1 over 30th. That's 3 over 30. Flip both sides. It's 30 over 3, which would be 10. Okay, so this whole thing is worth 10, and that's encouraging because when I do one of these, this answer I get for net should be less than the smallest one there. So here's what I'm going to do. I'm going to take this parallel structure and I'm going to replace it with a single resistor equal to what it's worth. So those two things together only provided 10 ohms worth of resistance. I'm just going to replace it with 1. Now over here I have a 10 and a 30, and you must go through the 10 and then you must go through the 30. So I could just replace those with a 40. So that's a little simpler. Well, I see here I have a 40 and a 20 in parallel, so I'm going to do this to get rid of them. Let's make myself some space. So 1 over RT is 1 over 40 plus 1 over 20. That's another easy one. I just have to double that. 1 over 40 plus 2 over 40 be 3 over 40. Flip both sides. 40 over 3, which is approximately 13.333. I'm just going to keep 3 decimal points. I'm not going to bother with fractions. This is complicated enough. So this 40 and 20 wired in parallel were actually worth the same amount as a 13 ohm resistor. Okay, now if I go down this path, I must go through this 13.333 and I must go through the 25. So I can collapse those two things using the series rules. It's just going to be this plus this. Be 38.333. All right. Now if I come here, I see 2 branches. I go through this or that. So that's a parallel structure. So I'm going to erase my space here. And then I'm going to add those 2 together as parallels. So 1 over RT is 1 over 38.333 plus 1 over 10. 1 over 38.3333 divided by 38.333 is 0.026087, and this is 0.1. This plus 0.1 will be 0.126087. RT comes up. This number goes down. This divided by this. .931 ohms. So this structure here, I can replace that with a single resistor that's only worth 7.931. Now this is getting considerably simpler. I think if I look at that circuit, I have reduced it down to entirely components in series. So I did all that work to do number 1 here and number 2 to redraw it so that I could see what was in series. And now I'm down to step 3 finally, which is just add the total. So all this mess up here, even though it had, well, I think it had 7 components when I started, is only worth 9.31 ohms of resistance. So those 7.93 plus 40 plus another 10 gives me a grand total of 57.931. I did this plus that equals 57.931. So that monster circuit that I had drawn there, I've now figured out the total resistance. And now that I know the total resistance, if I knew the voltage that was attached to this circuit, I could calculate the current that would flow through it. And once I have the current, then I can start dividing the currents up and dividing the voltages up to see how much of each component in the original circuit absorbed.